Okay, in the last video we learned how to simplify radicals, and now we're going to do a few more examples of that just to make sure that we all have the idea down pat. So here we have the square root of 12 p squared q. So again, we're going to separate out if we can, because 12 is not a perfect square. So I need to think of two things that multiply together to get 12. One of them should be a perfect square. So 12 could be broke down into 4 times 3, and now we could take the square root of each one of those. That's kind of using that reverse product rule there. Now we could also separate out our p squared and our q. So I'm going to go ahead and separate each one of those. Now as you get much better at these, you won't have to draw all this out every time. You'll be able to do a little bit of this in your head. But until you get to that point, there's no harm in writing it all out. Okay, let's see what we can take the square root of. The square root of 4, we can do that. The square root of 4 is 2. We can't take the square root of 3, but we can take the square root of p squared. That would be a p. And because we're doing an even root, we have to make sure and use the absolute value bars just to make sure that this will be a positive number. We can't take the square root of q because it's not a perfect square, so we have to leave underneath the radical the 3 and the q. So fully simplified, this would be our answer. Okay, let's look at this one. This one's very interesting, and there is a major shortcut way that you can look at this. But before we do that, I want to go ahead and write it all out so you can see how and why that happens. Remember, whenever we're working with numbers, we need to rewrite this as a product, and one of those should be a perfect square. Well, looking at y to the 13th, the perfect square, because this is a square root, I would have y squared. I could keep breaking that down into y squareds, couldn't I? So y squared times y squared, on and on and on and on and on. Let's see, how many is that? 2, 4, 6, 8, 10, 12. I need one more to be 13. Okay, now I could literally break this down into these smaller perfect squares and then times y. Each one of these perfect squares, the square root of the square undoes itself, and that leaves us with a y. Each one of these will actually when we take the square root, it will be y. So we should have 1, 2, 3, 4, 5, 6 of those y's, and then we still have this one single one that has to stay underneath the radical because it's not a perfect square. Now if I rewrite this, this would be y to the 6th and then the square root of y. This is actually our answer here. Now there are a couple of things going on. First of all, we do not have to write the absolute value bar this time. And the reason that we don't have to is because I'm raising this variable to an even exponent. So it doesn't matter whether this number is positive or negative. Once we raise it to the 6th power, it will always be positive. So we don't need the absolute value bars like we did over here to make sure it's positive. The 6th power will make sure that it's positive. Now the second thing was a shortcut way that I wanted to show you. If you'll remember from whenever we were working with those fractional exponents, we could rewrite that as y to the 13 halves power. True? Well, and then we talked about also before that we could really literally divide the index into the power because of this idea. So let's look here at what's going on. We have 2 divided into 13. That will go 6 whole times with 1 left over. So we could have went straight from looking at this problem. We could have said, well, 2 goes into 13 6 times, so that's a y to the 6th rather. And then we'd have 1 left over that would have to stay underneath the radical. We would still get the exact same answer, but this is a little bit of a shortcut way of looking at it.